This is a hydrofoil boat. Its name is Great Expectations. The principles by which it operates portend a new era in ocean-going transportation. This is the HS Denison, the world's largest ocean-going hydrofoil vessel. Commissioned as a test vehicle by the United States Maritime Administration, it has been designed and constructed by the Grumman Aircraft Engineering Corporation at Bethpage, Long Island. Its launching date is set for the summer of 1962, at which time the world will look on with great interest. For the success of the Denison, weight 90 tons, anticipated speed 60 knots, safety factor Sea State 5, will undoubtedly affect the future of commercial and military navigation. Grumman's more than 30 years' experience in the manufacture of amphibious aircraft has found direct application to the challenges of hydrofoil design. Familiarity with the hydrodynamics of these flying sea vessels and the problems of water tightness, stability, and control in rough seas has facilitated hydrofoil development at a rapid rate and low cost. In 1952, the XCH-4, an experimental vehicle constructed for the Office of Naval Research, demonstrated foil-borne speeds in excess of 75 knots. A destroyer in a beam sea is extremely susceptible to wave action. Hydrofoils are effective in dampening a vessel's motions in a sea wave. They allow it to lie quietly without strain to the hull or personnel aboard. In flight, with the foils submerged below the water's surface, the craft's stability and freedom from wave impact are demonstrated. Under contract to the Office of Naval Research, the next important experimental craft tested by Grumman was the XCH-6. The jet engine in this aluminum craft is a General Electric T-58. Using this engine, marinization coatings, the proper materials to resist saltwater damage, were developed. To get the vehicle in the air and gain proper flight trim, the pilot controls the throttle and the tailfoil's angle of incidence. Once up, he selects the speed at which he wishes to fly. And the vessel remains stable under these conditions. To land, the pilot reduces forward velocity by coming back on his throttle. The vessel then lands by herself. With the experience gained from these craft fully analyzed and evaluated, Grumman undertook construction of the HS Denison under contract to the United States Maritime Administration. This boat is Great Expectations, a 1/5 scale model of the Denison built to serve as a dynamic test model of the larger ship. Intensive study of the takeoff and flight characteristics of this manned model continued even as the Denison's final designs were being drafted. The vessel is autopilot controlled. The flaps of the forward subcavitating foils, operating in conjunction with the fully movable variable incidence tail foil, provide the pilot with mastery over roll, pitch, heave, and yaw. Construction on the 104-foot ocean-going hydrofoil ship commences. The frame of the Denison is a welded structure with the skins riveted to the exterior. The closeness of the frames is an indication of the hull's strength, as it is stressed to allow operation up to speeds of 80 knots. Concurrent with the building program, constant testing continues to provide information for the Denison and future hydrofoil vehicles. Grumman's whirling tank facility permits engineers to study the hydrodynamic characteristics of foils flying at velocities up to 100 knots. A strain gauge balance measures lift, drag, and side loads, together with pitching and yawing moments. Full-scale values of cavitation number and Froude number are simultaneously attained. The pendulum facility has been developed to measure hydrofoil loads and moments at speeds of 25 knots or less. As part of the overall study of hydrofoil construction, investigations into the flutter characteristics of struts are undertaken at Langley Field, Virginia. Here, the high-speed camera reveals the remarkable effect that velocity and water can have on a hydrofoil strut, this effect being yet another challenge which the engineers must face and overcome with each new design. The Denison has been framed out, skinned, and decked over, preparatory to transfer to the shipyard. The colorings on the vessel represent the prime metal protection system, zinc spray on the bottom and a polyurethane paint on the top side. The steel tail strut will support the gearing for the over-the-stern drive. Housed in the lower pod will be the lower gearing, propeller shaft, and variable incidence tail foil. The transmission system for the over-the-stern drive was developed by General Electric at Lynn, Massachusetts. A simulated gearbox was built to study tooth patterns of beveled gearing. After studying these imprint patterns, corrections can be made prior to installation in the strut. A General Electric MS-240 gas turbine engine will propel the Denison. It is a J79 jet engine with the afterburner removed and a free turbine coupled to it. While only 7,500 horsepower will be required for smooth water operation at 60 knots, maximum engine rating is over 18,000 horsepower to allow a large power reserve for rough water testing. The propeller for the Denison was a project of the David Taylor Model Basin in Maryland. This is a model of the supercavitating propeller that will be used. It is put into the test tunnel where propulsive efficiencies are experimentally determined. The propeller of the Denison will be able to develop over 35,000 pounds of thrust at a forward speed of 60 knots. The main foils of the Denison are steel structures weighing about 5.5 tons each. They are hung from hinges, which incorporate structure designed to shear under specific loading conditions. Since the foils are exterior of the hull, severe impact will cause them to break clear of it, creating no damage to the ship proper. 2 water jet propulsion units will steer the ship when it is waterborne. A high dead rise of the hull design will minimize wave impact loads. Hydrofoil retraction is accomplished by means of hydraulic actuators. The skipper of the Denison checks on the ship's progress. In a short while, he will be taking her on the first trial run. The interior of the vessel will be used essentially for payload, since the main engine and shafting are located on the main deck. The after-engine compartment contains the T-58 gas turbine engine, which drives the water jets for displacement propulsion. The saltwater system provides for ballasting, bilge eductor pressure, transmission lubricating oil cooling, sanitary and deck hose services. To meet weight requirements, aircraft equipment and components are used throughout. The hydraulic retraction system permits the raising and lowering of the main foils whenever required, whether for leaving or entering port, or laying alongside. All systems are color-coded for ease of identification, such as purple for JP5 fuel, red for firefighting, light blue for fresh water. The entire vessel will be operated by a 5-man crew stationed in the pilot house. All systems will be operable from the bridge. The captain and first officer will fly the vessel. They will start the main engine, the auxiliary engines, and handle the instruments necessary to control the flight and direction of the vessel. Soon, the HS Denison will make her maiden flight. A new era in ocean navigation may well be opened to the world as a result of this ship's performance.